Good evening. I'm Yvonne, staff for Science for the Public, and I welcome you to tonight's Contemporary Science Issues and Innovations program. One of the most enduring mysteries of our universe is dark matter, and our guest, cosmologist Julian Munoz, is involved with recent discoveries that may lead to an explanation. Dr. Munoz is a postdoctoral fellow in physics at Harvard University, where he's collaborating with leading scientists in a rather unique investigation that has attracted a good deal of attention: how dark matter might interact with ordinary matter. Along with that discussion, he'll talk about some of his other cosmological interests, including gravitational waves. We're delighted to welcome Dr. Julian Munoz. Welcome.
Thank you for having me.
Good. And if you will start us out just with some background about this dark matter issue, sort of how much of it there is and why it's a kind of mystery.
It is a good question. Dark matter has been a mystery for about a century. It's been since early 1900s when people started looking at motions of stars in our own galaxy, and they realized that the stars moved faster than they should, just given the regular matter that we have around us.
Yeah.
And this indicated that there's other matter that is pulling gravitationally the stars.
So there's no question there's something else out there.
That's right.
Right.
And this is true in the scale of our galaxy, but it's also true in much larger scales. So, for example, when we look at the cosmic microwave background, which is the light that was emitted in the first instance of the universe when the universe first became transparent, we can see the gravitational potential due to the regular matter, but also due to the dark matter. So we can infer that it's actually about 5 times more dark matter than regular matter. So not only is it mysterious and dark, it's also
much more of it.
That's right.
Yeah.
Which in some way makes it easier to detect. That's why we're fairly sure that there is dark matter.
Okay.
But it makes it that much more poignant that we cannot know what it is.
Right. So it's been frustrating for quite a while. So there's no question that there is such a thing, but we don't know what it is.
That is right.
So it seems as though there are like several candidates. Well, maybe people have heard of WIMPs, for instance, things.
Right.
What are these candidates, and can you tell us anything about those?
That's right. So I would separate them in 2 broad categories.
Okay.
You got the what you call particle dark matter. So
Yeah.
WIMPs, or
Yeah.
the weakly interacting massive particles, are particles that are not all that different from particles in the standard model. They just interact weakly, which is why they are dark matter.
Okay.
Dark meaning they don't emit light or any
Yes.
other light-like thing. Things that are also particles are axions.
Yeah.
Axions are predicted by different types of string theory or different theoretical models, and they are essentially similar to the standard model particles, but they have very, very tiny masses. In that case, they have a coherent behavior on very large scales, which is why they would be interesting cosmologically. They can have wavelengths that span a galaxy. And this is the way people look for them. And the other broad category that is not particle dark matter are things that you would call massive compact objects. For a while, we thought that dark matter could just be something like brown dwarfs, because we had only seen
so many of them.
Right, there's so many of them, and we had only seen dark matter in our own galaxy. Now we know that cannot be the case, because there has to be dark matter in the beginning when the cosmic microwave background was emitted. But there are other candidates that look like it. One of them are primordial black holes, and we might be able to talk about them later.
Yeah.
But in general, the idea here is that instead of being a particle, dark matter is some sort of congregate of regular matter that just doesn't emit light.
Yes, okay.
Like
That'd be like the brown dwarfs or black holes, right?
Exactly.
Okay.
So you don't have to have new particles, you just have to have a way to pack our regular particles in a non-emitting way.
Yes. Just real quickly, I thought that the dark matter had been detected around like galaxies and so forth, and that is by observing galaxies and the movement of stars, therefore they inferred the dark matter. What about these huge voids in the universe? Do you expect dark matter there as well?
Indeed, you do. I mean, voids are void. They don't have a lot of matter, but they do have some matter.
Yeah, I understand.
And people do find what is the density of voids, and you of course also see that there is more matter than just regular matter, so there is dark matter.
Right.
In fact, I'm glad you pointed out. I want to show this slide. This is the bullet cluster. So it's a cluster of galaxies.
Okay.
So this every one of those little circles is a galaxy roughly like our own. And the red and blue are maps of where the X-ray emission comes from. So red is X-rays. So that's where the gas, where the regular matter is, right? And the blue is where the mass is.
Okay.
So you see that they don't coincide at all.
Right.
So what happened here is there were two galaxy clusters. So two clusters that are made of different galaxies, gas, and dark matter.
Right.
And they collided with each other. And when they collided, all the regular matter, which interacts with each other, got stuck near the center. So that's the red. But the dark matter basically pushed through because it doesn't talk to each other that much.
Yes, right.
So you see dark matter is in a different place than regular matter. So not only we have dark matter, and not only we know that we have 5 times more than regular matter, we also know that it's an independent thing. You cannot just modify gravity in a way
to get that.
to give you this.
Right.
So we have all this confirmation from galaxy scales, cluster scales to the CMB. They all point to the same conclusion. There is dark matter.
Right.
There's about 5 times more than regular matter.
Okay.
So the question is,
what is it?
What is it?
And how do we get a handful of it or something, right? Okay. So why is it so difficult?
It seems that nature has not been kind to us in what dark matter is. We had a very clear theoretical prior. The reason why WIMPs were a big deal is because we expected that they would work, and we thought they could be dark matter, and a lot of effort was put in trying to find them. There's all the underground detectors to find WIMPs.
Yes.
And they are all exquisitely precise, and none of them has found dark matter.
Okay, all right.
Out of the space of possibilities where dark matter can be, it is not in the obvious place.
Okay, all right, so WIMPs are out now, I guess.
The regular canonical WIMP that people in my field would call the WIMP, it is out. There are lighter WIMPs, things that can have about the mass of the proton or lighter.
I see.
Where those are not entirely ruled out. And in fact, there's a lot of experimental effort to reproduce the direct detection constraints that we have for very heavy WIMPs. So all these mines underground, you might have heard they have like the xenon experiment, dark side, they'll have some noble gases. So you have some noble gases where they are not supposed to do anything. You just wait for a dark matter particle to come in, kick one of them, move it, and then you can see it.
But this isn't happening.
We haven't seen this so far. People are trying to reproduce this for much lighter dark matter.
I see, I see.
Then you wouldn't see the kick because the matter is so light that it doesn't move it. And there's a large amount of experimental effort on this front.
Right.
But precisely because we have not seen the canonical WIMP, the typical dark matter candidate that you would expect, now we are looking for things that might be a little less obvious, a little less canonical.
In your mind, there is a way to find it, right? You expect one of these days they're going to come up with the right solution.
I think yes, I think that's correct.
In other words, it's not something that is permanently out of reach.
Yeah, I don't think so.
Okay.
We have a very clear handle from mathematical principles.
Yes, I understand in terms of it exists, but it's so difficult to.
But even in terms of what candidates are possible, there are some mathematical guidelines.
I see.
It cannot be some arbitrary. It has to follow the rules of quantum field theory, which we understand fairly well.
Yes, and it's very accurate, I think.
That is right. So that's why we can predict whether dark matter. Not predict, but rather we can posit that is something like a fermion.
Right.
So a spin 1/2 particle like protons or electrons.
Right.
Or can be a scalar like an axion.
Okay.
So we have a finite amount of possibilities, and some of them might take decades to entirely rule out.
Yes.
But there is a clear way forward.
So you're saying that in terms of at a theoretical level or something, we're really very sure here, but in terms of the things that would actually catch it for you and identify it for you, that is still out of reach. That's the thing that's really out of reach, isn't it now? Okay, so what would you need to find it at this point? Is that?
I think there are possibilities that you could, that are already happening within maybe a decade. You'll have a very clear picture whether it is some of them. So the axion searches, for instance, are moving very fast.
Okay.
Things like, as I said, low mass WIMPs are also moving fast. There are some other candidates where nothing, no experiment you can build on Earth would detect them.
Right.
So primordial black holes would be one of those candidates.
Yes.
There's no new particle.
Yeah.
It's just regular matter that assembled itself into black holes in the very early universe.
Yes.
And there, what you have to do is you have to resort to astrophysics.
Yes.
And astrophysics gives you a very clear indication of whether matter are primordial black holes or not, related to gravitational waves. And this is something that I've worked on in the past, and we can talk about later if you want.
What we don't understand about the primordial black holes is how could they get matter before you had atoms, I'm assuming, or did they appear after we had atoms? They were there before. Okay.
And the way it would work is, we know the universe where we're now is expanding.
Yes.
So if you take the movie backwards,
yes.
we've all heard this picture, it gets denser and it gets hotter.
Yeah, right, okay.
At some point it's hot enough that atoms cannot exist.
Right.
So all the electrons and protons separate.
Yes.
And instead of hydrogen atoms, you just have electrons and protons. If you go even farther back, protons are made of quarks.
Yeah.
And at some point the quarks separate.
Yeah.
So you have a hot quark gluon plasma.
Yes.
So presumably what could happen that will lead to primordial black holes is that some parts of the universe are very dense.
Okay.
So you can think that there's different patches of the universe, and we know that these patches are not connected to each other. They don't talk to each other. So some of these patches are very dense.
Yes.
And then just from their own gravity, they collapse into a black hole.
Okay. All right. Good stuff.
So let's go sort of the way on the left, the Big Bang, where we don't really know what happened. What we know is that, as I said, the universe was hot and dense. Maybe some part of the universe collapsed into a black hole, maybe not. But we know that at some point, as the universe expanded, it became cold enough that protons and electrons were able to combine and form atoms, hydrogen.
So this is the period.
That's recombination.
Okay.
That is the weird red and blue dots over there.
Yeah.
That is a cosmic microwave background.
Okay. All right.
Which, when you combine all these hydrogen atoms, then suddenly, for the first time, light could move.
Yes. Okay. So we get the transparency thing. Okay.
And this is the 2.7 Kelvin background that we have nowadays. For a long time, we had what we call the cosmic dark ages.
Okay.
All there was in the universe was neutral hydrogen.
Yeah.
As I said, hydrogen doesn't really emit that much light, although we'll see in a second that it can do. So they are dark ages because nothing is emitting light. You just have the CMB, nothing else. Until about a few 100 million years after the Big Bang, you have the first stars being formed.
Okay.
These first stars, as we'll see, emit a lot of photons, and they excite hydrogen atoms.
Yes.
And this is what we call the cosmic dawn.
Okay.
When you get out of the dark ages into the day that is the universe
Eventually
nowadays.
it becomes transparent, or is that later?
It became transparent at recombination.
Okay.
And what is happening now around the epoch of the first stars is that you have photons that allow the hydrogen to do things.
Okay.
And we'll talk about this in the next slide.
Okay.
And then you have galaxies, like sizable objects, the first galaxies form, and then they actually ionize the hydrogen again.
Okay.
So this hydrogen that has been neutral since recombination, there's enough UV photons to again take the electrons out.
Okay.
Have just protons and electrons in the universe. This is what we call reionization. And then the universe is just electrons and protons until now.
Yes.
Well, of course, you form galaxies.
Yes.
With modern galaxies here, they mean galaxies that are Milky Way sized.
Yes, okay.
Not tiny galaxies that formed
so
earlier.
Those earlier ones were tiny.
That is right. Basically, see, galaxies grow and grow as the universe progresses, as they accrete matter and they become bigger.
All right.
And all these lines here are, you see that in the right, the little telescope is the Hubble Space Telescope. And it has actually been able to see galaxies up to redshift 8, which corresponds to about 13 billion years ago.
It's amazing.
It is. And they do this through the Hubble Ultra Deep Field, you might have heard of,
yes.
where they look at a patch for a very long time, an empty patch. And after integrating for many, many hours, they see these dim galaxies so far away.
That's amazing, yeah.
And on the left, you see the JWST, the James Webb Space Telescope, which is going to commission next year.
Next year.
Which will push it even further to see the first galaxies formed.
That is amazing.
So not only we have a theoretical picture, this is all, of course, this is an illustration, we actually have clear indication from telescopes that this happens.
Okay.
And getting back to the hydrogen, what it does and doesn't do, this is roughly the same plot as before.
Yeah.
So, the right is to today, the left is earlier in the universe. And what happens, the hydrogen has a 21 centimeter spin flip transition.
Oh.
So if you have hydrogen, it's a proton or an electron.
Yeah.
It has, they're both spin 1/2 particles. So they can have spin up or down.
Yes. Okay.
It turns out that if the two particles have the same direction in the spin, they have a slightly higher energy than they have in opposite directions. This has to do with the fact that when they orbit each other, they have angular momentum.
Okay.
And spin is a
right.
way to have quantum angular momentum.
Okay. Right. Okay.
So if you have hydrogen this way, it will naturally try to get to the lower energy state.
Okay.
And when it does this, it emits a photon.
Ah.
It's the same way that regular electronic transitions.
Yes.
These are called hyperfine transitions.
Okay.
And the typical wavelength of this is about 21 centimeter. So you might have heard a 21 centimeter line of hydrogen.
Yeah.
It always means this spin flip.
Okay.
Now what happens is these photons, imagine you emit this at a very high redshift, so very early in the universe. As the universe expands,
Yes.
the wavelength redshifts becomes longer.
Yes.
And that's how we measure age, usually,
Yes,
by how
right.
redshifted are the photons.
Yeah.
So this 21 centimeter becomes longer and longer and longer.
Okay.
So if you have 21 centimeter from about redshift, say 100, it will become a 21 meter transition.
Yes.
So in those wavelengths, we don't talk about wavelength, we talk about frequencies. Those are comparable to the FM that you can see. So here in the bottom axis, you see they have frequencies in megahertz.
Yes.
So each of these frequencies corresponds to a particular instant in the universe, given by the redshift that is in the upper part of the plot.
All right.
So again, going from left to right, at the very beginning on the left, what you have is when the cosmic microwave background is emitted, is recombination. Since before then there's no hydrogen, so there's no spin. For a while, hydrogen could absorb CMB photons in this particular 21 centimeter line.
Okay, all right.
So the CMB has photons at all frequencies. The CMB is a black body,
yes,
that's what we call.
Right. The CMB is cosmic microwave background,
yes.
Okay.
The cosmic microwave background, the CMB, the cosmic microwave background, has photons at all wavelengths.
Right.
So some of those happen to be at 21 centimeter.
Okay, just very quickly, if you would just explain what does that CMB mean?
Right, so when the hydrogen first formed, so electrons and protons got together, the light could travel for the first time. And in reality, it mostly looks like a background that's constant in the sky with about 2.7 Kelvin today. In reality, once our measurements got really, really good, we were able to tell that there are small anisotropies. So if you look at the plot I showed before on the left, all the blue and red, that's part of what it will look like in the sky.
Just teeny weeny differences.
Teeny, about 10 parts in a million.
It's okay.
And what is causing that are a lot of effects, but mostly gravitational potentials from the regular matter and from the dark matter. So that's one of the ways we know there's dark matter, is that when the photons have to climb up from the gravitational potential due to dark matter, they have slightly lower energy, which looks like a smaller temperature, looks blue.
All right. So you really have a lot of evidence there.
We do have a lot of evidence, that's right.
Okay, yes.
And so these photons from the CMB have all sorts of frequencies and wavelengths, and some of them are in exactly a 21 centimeter transition.
Yeah.
And then those can be absorbed by hydrogen on the way.
Okay.
So when we looked at how many photons there are in the CMB, we'll see missing photons. So this is the way that we will look for the 21 centimeter line of hydrogen. And now, what they're plotting here so the upper part is an illustration of what it will look like in a simulation. And the bottom line is the average. So we start on the left. In the dark ages, you see that the line is slightly below zero at about minus 50.
Right.
That's millikelvin in units, just for the record. So what happens there is that the hydrogen can interact with one another.
Okay.
So this, the populations of singlets are given by the temperature of the hydrogen, which is colder than the CMB. The CMB is hot photons. So you actually lose CMB photons.
Okay.
But as the universe expands, the hydrogen doesn't talk to each other all that much.
Okay.
So that becomes inefficient, and the line goes up again near zero.
Okay.
So then you stop seeing this.
Yes, all right.
Then, at some point, you form the first stars in the universe, the first galaxies. And as I said before, they emit UV photons and they excite the hydrogen. So then again, this becomes possible. This goes down, you have absorption.
Right.
At some point, you emit X-rays.
Yeah.
X-rays are very good at heating up gas because they can travel much farther.
Okay.
So X-ray photons tend to interact less with regular matter, at least, on average. So X-ray photons travel farther from their sources, so they can heat up homogeneously the universe. So then the temperature goes up, and at some point, you see, we go to what we call reionization.
Yeah.
Where there's so many photons that, again, electrons and protons separate.
Okay.
As we mentioned before, and you end up with just, there's no hydrogen, there's no 21 centimeter line. So that's the entire history of 21 centimeter.
Yeah.
And the new thing to this theoretical calculations have existed for decades, is that now we have detected it, or we think we have detected it, because the EDGES collaboration, where EDGES stands for Experiment to Detect the Global Epochal Reionization Signal, has actually seen this dip over here where it says heating begins.
This is where you've been involved. This is
in the theory side. I'm not an experimentalist.
That's right. Yeah. Give us an idea. This is what we would like very much to know about this.
Right. So what we have, what EDGES, the EDGES collaboration has reported, is this absorption at about redshift 20. So, frequencies of 70 megahertz.
Yes.
Which corresponds to dozens of millions of years ago.
Oh, yes.
Almost like 13 billion years ago.
Yeah,
It's a very early universe.
Right.
They have reported how we're missing CMB photons in a way that is consistent with 21 centimeter absorption.
Okay.
And the striking fact is not that they have just detected it, that the absorption is much deeper than you would expect. So instead of getting down to minus 100, it actually goes down to minus 500.
And that is caused by?
And that is where the dark matter part comes in. The only way to make this work that we can think of is by having dark matter cool down the regular matter. The colder the regular matter is, the lower this line goes.
That sounds very significant from this angle then. So that sudden drop it's an indicator of something highly significant, and you're saying the logical thing is the dark matter.
That is right. If the EDGES result is right.
Right.
One of the few ways to reconcile it with astrophysics and physics is to have dark matter steal energy from the regular matter, so that line can go lower.
Okay, all right. Would there be other alternatives? Because the EDGES thing still, I'm sure, has to, be disputed, and the people have to. It takes time to determine these things once you get a good theory out there. So here's a hypothesis for now, but it sounds very tempting. The
biggest challenge from the observational side are foregrounds, because you have the same radio signal in the tens or hundreds of megahertz is emitted by hot electrons in the Milky Way.
Okay.
They emit synchrotron radiation when they travel in magnetic fields.
Yeah.
And there's an overwhelming signal. And the way they go about this problem is they marginalize over foregrounds, and people might have concerns about how you do that. So I would say the signal is very tempting.
Yeah.
But it will have to be reproduced by other groups.
Sure.
And thankfully, there are other collaborations.
Right.
The interesting part is this 21 centimeter science is still in the infancy to some extent.
Okay.
The EDGES collaboration, for instance, was half a dozen scientists.
Oh, is that so?
It's a very small collaboration.
Yeah.
And they were able to deliver an extremely important result, which, if confirmed, is
that's dynamite, isn't it?
It's not like the LHC or something. Particles where you have hundreds or thousands.
Exactly.
6 people.
Yeah, right. That is amazing. That is amazing. But it seems like, like discovering the Higgs or confirming the Higgs after a long while, or gravitational waves after a long while, this might be right in there, that sort of thing, because this is a big issue, the dark matter thing.
It is. So what we realized is that we first heard of the signal before getting to work on the theoretical side. And we realized that there are ways to make this work. There are ways that dark matter can steal energy from the baryons.
Okay.
And the one we found that is the most promising is to give the dark matter a tiny electric charge.
Yes, I think that's the hardest thing to understand myself. Please tell us about that.
So the way this would work is we usually would think of dark matter as some exotic, strange thing.
That's right.
Maybe it's very heavy. That's why we
Doesn't
see
interact.
it.
Yeah.
Maybe it doesn't interact. Maybe it's something weird. But in some ways, it's kind of natural that it would interact through one of the forces that we know.
Yeah.
So we know that it interacts through gravity.
Yeah.
That is how we locate it.
Yeah.
We are fairly certain that it cannot interact with a strong force because that is a very strong force.
Okay. Yes.
So the WIMP, for instance, the weakly interactive massive particle, it was thought that it would interact with a weak force. That is why it's a WIMP.
Okay.
Although that was discarded quickly because we would have seen it.
Right.
So one way you can make it work is go through the fourth force, the electromagnetic force,
Yeah.
which we understand really well. And in that case, what we can say is if dark matter doesn't have unit charge, like the electron, doesn't have the same charge as the electron, it's much less charged.
Yes.
In that case, we wouldn't have seen it in accelerators. We would not have seen it anywhere else.
It would be very hard to detect, evidently.
That is right.
Very, very hard.
And just to have an idea, we're thinking of charges that are about a millionth of that of the electron.
Right. Okay.
If the dark matter is so feebly charged, it is almost impossible to see in accelerators.
But it's still meaningful, even though it is so minuscule.
And what happens is during this era, as I said, when the curve dipped down, the baryons are the coldest that they're ever in the history of the universe, since they get heated by the X-rays later.
Got it.
Cold particles interact a lot through electromagnetism.
Oh, okay.
So if dark matter was charged,
Yes.
that would be the first place you would see it.
It sounds better and better, every sentence there.
And what we proposed is that these particles with about 1 to 100 times the mass of the electron, about a millionth times the charge of the electron, could be explaining the edges signal. They could be the cause of this anomalous cooling, this deep signal. And if so, then that would mean that we found at least part of the dark matter.
Right.
It's unlikely they will be all the dark matter since they're very light and they will get trapped in magnetic fields.
Right.
But they could be a very important part of it. And the rest of the dark matter could talk to them the same way that electrons are a very tiny part of our weight as regular matter.
Yeah.
But we talk with the electrons.
Right.
And I think perhaps the most significant thing to come out of it is even if you don't believe the signal, even if the signal goes away, and it happens to agree with our expectations, these measurements of 21 centimeter at the cosmic dawn, when the first stars formed, have the most potential to detect these particles. They're stronger than any accelerator we can build on Earth right now.
So you really can't, yes, okay.
Right. The fact that you can see them better than an accelerator means that you can actually constrain them if the signal was to agree.
Okay.
So in the quest for what is and is not dark matter, 21 centimeter really seems to have the key to understand.
That's very exciting.
Yes.
What's the status now? It's new, right? I mean,
it is new. The results are from...
and you're waiting for other teams to sort of...
Right. So the EDGES team themselves have a different instrument they're testing. There are groups here in Harvard. There are groups in India. There are different groups across the planet that are trying to reproduce the results.
Okay.
Nothing has come out yet.
Right. I understand
so we don't know.
Right,
we don't know
you just
yet.
bite your nails for a while.
Right. But it is expected that within a year, perhaps 2 years.
Oh, that's
most,
soon.
Yes.
Oh, that's exciting. Is that because of that mysterious dip?
That is right. The deeper it is, the easier it is to observe.
Yes, right.
The next step is seeing the fluctuations in that signal.
Okay.
So the same way the CMB is these photons with 3 Kelvin temperature and then it's minuscule fluctuations.
Yes, right.
The same is true for this.
Okay.
You will have the average signal, which is hundreds of millikelvin, and then you'll have fluctuations of about 1 part in 1,000 instead of 1 part in a million.
Yeah.
But still, tiny fluctuations in the sky.
Right.
And that is the frontier. That is where we want to get.
Yes.
Those fluctuations would not only tell us what is the average of the signal, but where is it hotter, where is it warmer?
Yeah.
What are the regular matter particles doing?
Yeah.
And that is extremely important to understand if dark matter is interacting in any way, to understand how the first stars formed,
Yes.
when they formed.
Right.
And that sort of project really requires a big team.
Right.
So for instance, in MIT, there's this big experiment called HERA, which is a collaboration from different people, but MIT is one of the leaders. They will be able to detect this signal from the epoch of reionization, so from later, from when the electrons and protons are separating.
Right.
that would be extremely exciting. And if we were able to detect that signal during the cosmic dawn,
okay.
then we would actually see that critical time in the universe when dark matter might be.
Really, yes.
Yeah, it is very exciting.
Yeah.
And that actually does require a big team and hundreds of antennas, as opposed to one antenna.
Right, and a whole lot of brains behind that one. Right. You have a diverse set of interests in all of this, so I want to ask two things. How did you get into this in the first place? And then you have several interests that I'd like to ask you about. Okay, so how did you get into it in the first place? You're from Spain?
I'm from Spain. I came to do my Ph.D. in the U.S., Johns Hopkins University.
Yeah.
And the guy that I was most interested in working with was a cosmologist. So he gave me some toy problem, and I worked on it for a while, and I realized I really liked it.
This is it.
And I was hooked.
Yeah, it's easy to understand. It really is.
It is, and it is. There's a lot of technical parts to it, but at the end result, you're studying the universe, which it's by definition interesting.
Right. And you had other things that you were interested in. You were interested in gravitational waves and the primordial black holes.
That's right. So before, years ago, when LIGO first detected gravitational waves, there was another sort of puzzle that didn't turn out to be a puzzle, but the puzzle was that the first black holes we detected were very heavy. If you remember, they had about 30 solar masses each in weight. And that is a number that we were not expecting.
That these earliest would be so heavy, did you say?
That any black hole that we would see.
All of them were, okay.
All black holes that we had seen before, we had seen them in X-ray binaries.
Okay.
So you have a black hole, you have a companion, and the companion is accreting matter to it, so it emits X-rays.
Right.
And these ones have masses of 5 to 10 times the mass of the sun.
Okay.
And that is what our models were also predicting.
Okay.
People run models for what the black holes do, and that is the number. And 30 is a very large number.
Okay.
None of the models at the time predicted 30. So we wondered if these black holes were not astrophysical. Black holes can be astrophysical, meaning they are the endpoint of stellar evolution.
Yeah.
And instead we wondered, what if they are the dark matter? And through some calculation, we showed that dark matter lives in halos, like the halo of the Milky Way.
Yes.
And every once in a while, two black holes that are the dark matter would come close to each other, and they would form a binary.
Yeah.
And this binary would coalesce, emitting gravitational waves, which is exactly what LIGO saw.
Exactly.
And when you calculate how often this happens, it works out to be about how often LIGO has been detected gravitational waves.
I see.
Which is why it was
they all go together.
Right. Which worked out to be an interesting coincidence. And it started a wave of thinking about primordial black holes again.
Yeah.
And I think at large, what can gravitational waves teach us about dark matter? And this is one clear example where if dark matter are primordial black holes, you wouldn't see them in any accelerator.
Yeah.
You wouldn't see them through direct detection.
Right.
You would have to look at the sky and see the gravitational waves emitted by these black holes.
Okay, and that's the only way to detect those.
Yes,
right.
That's right.
Okay, so that's the reason for that excitement. Another reason for being in this work at this time when so many things are happening. What do you predict in terms of like the next 20 years in developments here?
So I think by far the thing that I find most interesting are all these 21 centimeter experiments that are delivering results, and they're going to get much better.
Right.
But on different side, gravitational wave measurements are getting extremely good, and they're starting to detect events almost on a monthly basis.
Yeah.
Something that I also find very interesting, which is another sort of astrophysical event, are called fast radio bursts.
Oh, yes.
These FRBs, fast radio bursts, are entirely mysterious.
It's really mysterious, yes.
We don't know what is causing them, but we know that it's astrophysical.
Right, yeah.
We expect some neutron star, some very compact object with a very high magnetic field.
Would those be very distant in time? Would they go? Is that an indication of something from the remote universe rather than closer to us? FRBs
they are cosmological, as in they are maybe 1 billion light years away. But not far away enough that you would think of.
Right. So it's not necessarily a signal from the earliest universe
That's
by
right.
any means.
It's from the late universe,
yeah,
if you wish.
right, okay.
But again, we don't know what they are.
Interesting, yeah.
And I think we have detected a few dozen of them so far, because we've been looking with very small telescopes that were not designed for FRBs. They were looking
Yeah.
at a galaxy,
Yeah,
and it just so
there's a
happened to
thing,
go
right,
off.
yeah, yeah.
And these things, by the way, they're called fast radio bursts because they're very fast. They last
Okay.
about a millisecond.
So you really have to have the telescope trained on this. Is that the idea, to capture it?
The way they do it is it's radio, so they have detectors where
Okay,
they
yeah,
actually
yeah.
process the data.
Okay.
But you actually have to be looking at it. It's not like a galaxy that's going to be here today, tomorrow, and in a billion years. This thing
You
goes
see,
off.
they're so fast.
You have to be exactly looking when it happens.
Okay.
And now we're going to have experiments. There's the one called CHIME, it's Canadian Hydrogen Mapping Experiment, one called HYRAX, which is the same in South Africa. Both these experiments are going to be able to detect thousands of these FRBs every year, which means that we're going to have a very clear picture of where they are and perhaps where the properties are, and this should lead to us understanding where they come from, but also what can we learn about the universe and about dark matter
Yeah.
from them.
So you think there is a possible connection?
So something we realized is if dark matter was primordial black holes,
Yeah,
primordial black holes not only interact through gravity by merging,
yeah.
they can also bend light. So this is
Right.
called gravitational lensing.
Right, lensing.
And the way this works is that photons are massless, light particles are
Right.
massless, but they still follow the curved spacetime.
Yes,
So if you put a primordial black hole between an FRB and you,
right,
it will get bent.
yes,
And if it's right on the way, it can have two paths on the way to you.
yes. So it goes around there
Right.
like that,
So you
yeah.
might have heard of the Einstein arcs.
Yes,
When
absolutely.
things are gravitationally lensed, you see an arc around it.
Absolutely. And
For an
now
FRB,
it's common to see it.
It is common, yeah. We have hundreds of them. For these FRBs,
Yeah.
you wouldn't see an arc because they last a millisecond. What you would see is one image and then another one.
Yes, because it's, okay.
Because it does not emitting all the time.
Yes,
So we realized that these FRBs can actually tell us if primordial black holes are the dark matter or not
Okay.
by whether they are echoed this way, whether on the way to us they cross near a primordial black hole and they are lensed.
right.
And in fact, it will happen often enough if primordial black holes are the dark matter that about 1 in 100 FRBs should be echoed. So we only have 30 or 40 of them for now, so we cannot say anything. But within a year or two of operation of CHIME,
Yeah.
which is being built, or HYRAX, we will be able to definitely tell whether primordial black holes can be the dark matter.
This is really neat, isn't it? I think you have a lot to do in your lifetime here.
Hopefully.
Right, I think it'll keep you busy. But I really appreciate very much your giving us this fabulous information.
Thank you for having me.
I wish you the very best in your
Likewise.
career. And you'll have to come back another time to talk some about these things. Thank you again very much.
Thank you.